Welcome to the presentation of the work entitled Frequency Scaling in Multi-Level Queues. I am Andrea Marin from the University of Venice, and this is a joint work with Maryam Elahi from the University of Monte-Royal, Sabina Rossi from the University of Venice, and Carey Williamson from the University of Calgary. So this is the outline of the talk. We will begin with an introduction and a description of the contribution. Then we will present the QA model that we propose and its numerical solution. Then we will apply this result to a case study and we will draw some conclusions. So science-based scheduling. Science-based scheduling is an idea that allows us to reduce the expected response time in certain situations. And there are several assumptions when we schedule the jobs based on their size. And first thing, if we know the size of the job at the arrival time, then we can apply the shortest remaining processing time scheduling that is optimal for the minimization of the expected response time. If we know the distribution of the job size, then there are several other disciplines that we can apply, among which we know that the Gittins policy is optimal. The case in which we work is that we don't know in advance the distribution or the exact job size, and but we know that the job size is heavily tailed. In this case, we know that the least attained service is optimal in certain conditions, but it's sometimes hard to implement. So we will focus on multi-level queues, which can be shown by this picture for the case of two levels, which will be treated in this presentation. And for the case in which at the two levels we work with the processor sharing discipline. So the job size is divided in two parts. A high priority part, which is the part of the job that whose size is lower than a certain threshold A. And then there is a low priority part of the job, which is everything that exceeds this threshold A. So when a job arrives, it enters in the high priority queue and starts receiving service. When the level of attained service reaches a threshold A, the job is moved from high priority to low priority. And this is shown by the red arrows in the picture. The priority of the two queues is a strong priority, the hard priority. So the server works only on the jobs in the high priority queues, according to the processor sharing discipline in our example. And when this queue is empty, then it will start working as a processor sharing queue in the low priority. So the idea is that we don't know in advance the size of the job because we reason on the level of attained service. Clearly, the jobs that have a size smaller than the threshold A, they never go in the low priority, so they're all served with high priority. So frequency scaling. Frequency scaling is another idea whose goal is energy saving in the system. And the main idea is that when we have few jobs in the system, then we can reduce the processor speed without affecting too much the expected response time. So basically, we affect in a negative way the lucky jobs, so the jobs that arrive at the system and don't find other competitors in the queue. Why does this idea work well? It's because the service time is directly proportional to the service speed. So if we halve the service speed, we double the service time. But the power consumption depends on the service speed with the with exponent alpha, where alpha is usually considered to be between 2 and 3. So basically, the save that we have when we apply speed scaling is higher than the delay that we introduce for applying this technique. The linear frequency scaling is a way of doing frequency scaling in which the server speed is proportional to the number of jobs in the system. So this is a very short list of related work. You will find a more extensive one in the paper, but let's say that the frequency scaling applied with size-based scheduling has mainly focused on SRPT, so the shortest remaining processing time. And this has been studied under different perspectives. So from worst case analysis to the unfairness. In particular, we know that when we use SRPT with frequency scaling, the unfairness is magnified. And then there is some work where the least attained service has been studied in the context of the sleeping server. So we basically, with this contribution that we show, we basically cover this gap in which we study what happens in multi-level queues with the frequency scaling. In particular, we give a numerical solution for a queuing system in which the frequency scaling is applied only to the low priority queue, because basically all the effort we want to put all the effort in serving the small jobs, so the jobs with high priority. Then we study the behavior of the model for the case of jobs whose size has been taken from fitting some TCP flows. This is a graphical sketch of our model. This is a single server model, even if we represent it with two service rooms, but we want to emphasize that one service room works with processor sharing scheduling, and the second one instead is an infinite server, so it applies the idea of linear frequency scaling. And the job arrives according to a Poisson process with intensity lambda, and the part of the job which is smaller than the threshold is served with maximum speed in the processor sharing queue. Then, if the job exceeds, so it has not completed its service in the processor sharing queue, this is moved to another queue, which applies the linear frequency scaling. And this is basically modeled as an infinite server queue. Clearly, the base frequency of the infinite service queue will be much smaller than the one of the processor sharing. The infinite service queue works only when the processor sharing one is idle. So this basically implements the idea of the multi-level queues. The job size in our case is modeled with a generalized hyperexponential distribution. And what's the characteristic of this distribution is that with respect to the hyperexponential distribution, we don't require that the mixing parameters P are strictly positive, but they can be also negative. But we have this request that the density function must be positive on all the support of the function. So it's it may be difficult to check, but since we obtain this GH distribution beginning from phase type distribution, then we're sure that that condition is satisfied. The GH distribution are dense in the domain of the distribution, so they can approximate any distribution arbitrarily well. Let's sketch the analysis of the queue. The high priority queue works like an MG1 PS queue, whose job sizes are truncated at A. The low priority one is nothing more than an MG infinity queue with batch arrivals. The arrival process is a Poisson process with intensity lambda, and the batch size distribution is basically the distribution of the number of jobs that cross the threshold during a busy period of the processor sharing level. We know that the generating function of the batch size distribution of the processor sharing level has not an explicit form, but has a characteristic equation given by Klein-Rock. The solution of the ESQ requires the distribution of the batch size. So how do we compute the distribution of the batch size? Basically, we invert the generating function with the lattice Poisson algorithm by Abate width, and then the evaluation of the generating function is done with a fixed point algorithm whose convergence has been proved in the paper. The accuracy of the numerical procedure is validated in low and heavy load by comparing the first two moments of the distribution that actually has an explicit form for a GH distribution of the job size with those obtained by the numerical inversion. We resort to the literature for computing the power consumed by the PS level, which is very simple. And for the ESQ, we computed the following moments, so the second and the third moment, for the occupancy distribution. And in this way, we can compute the power consumption. So let's see the case study. So first of all, we took the data, we monitored for 1 month the TCP flows at the University Ca' Foscari of Venice in November 2019, and then we fit the distribution of the of the flows into a cyclic phase type distribution by using an existing tool which is called pH-fit. Then we transform the acyclic phase type distribution into a generalized hyperexponential distribution. This is the result of the fitting. As we can see, the distribution is heavy-tailed, and the fitting procedure is shown to be quite accurate. So let's start with the analysis. We assume that the PSQ has speed 1 and the infinite server level has speed f, where f is much lower than 1. Here we have taken f equals 0.05, f equals 0.10, and f equals 0.15. And here we see the ratio between the expected response time of the PS plus ESQ and the processor sharing for a load factor of 0.85 and 0.92. We can see that the expected response time is generally worse than the one of the processor sharing. It goes below 1, as you can see, for the load factor 0.92. And this happens because basically, if we take f equal to 0.10 or 0.15, the infinite level layer goes faster, and so sometimes it even crosses the speed of the processor sharing level. Anyway, we can see that we can achieve some power saving, even without affecting the expected response time. So basically, the benefits of the multi-level queue are balanced by the worsening down of the performance given by the frequency scaling. Here we can see that we have the threshold on the x-axis, and there is an optimal values of the threshold that we can set so that the power consumption is minimized. Here we can see the slowdown of the jobs. On the x-axis, we have the size of the job in number of packets, and on the y-axis, we have the ratio between the expected response time of the PS plus ES and the expected response time of the processor sharing queue. We can see that the smallest jobs have a smaller expected response time, so the jobs below the threshold, but then the frequency scaling mechanism increase a lot the expected response time of the jobs that cross the threshold. In this plot, we show the comparison between the expected response time of the PS plus ES and the expected response time of a simple infinite server queue or processor sharing queue. The power consumed by the TS plus ES is shown by the red line, and the power consumed by the ES and the PSQ are set up in such a way that are exactly the same of the power consumed by the PS plus ES. So the comparison is, if these three queues consume the same power, what's happened to the expected response time? Here we can see that according to the threshold that we choose, we may have some benefits, but sometimes the system PS plus ES works even worse than for instance, a simple infinite server queue, so which means that it's a system with linear frequency scaling. And so these plots show that the appropriate configuration of the queue is crucial for having benefits for this type of systems. Then we run some simulation. The simulation have been used to cross-validate the numerical results. And in particular, we have investigated some other characteristics of the system, such as the distribution of the system speed. So to conclude our presentation, we have introduced a two-level queuing system that we call PS plus ES with linear frequency scaling at the low priority level. We have shown a numerical procedure for the solution of the queue and its parameterization. In particular, we have shown that the model-driven configuration of this type of system is crucial for having benefits, because sometimes it can work even worse if it's badly configured than the simpler model, like a simple processor sharing queue or a simple infinite server queue. This is known for the for the multi-level queues, that the configuration of the threshold can be crucial for having benefits in terms of reduction of the expected response time.